Speaker is Professor Iwasawa.
Thank you, Mr. Chairman. I'm not sure this is correct or incorrect. Correct. Okay. I try to speak in Chinese. 我非常高兴见到你们。I'd like to talk about bimetallic substructures of highly active rhodium-tin silica catalyst for nitrogen monoxide dissociation and NO hydrogen reaction by excess and FTIR. At first, I'd like to talk about briefly the strategy of the present study. This is the previous literature reported by Professor Alex and his colleague. They reported NO hydrogen reaction mechanism on rhodium supported on silica, that monometallic rhodium catalyst. NO doesn't react on rhodium particles supported on silica by itself, at particularly below 100 degrees Celsius. NO molecule associatively absorbs on rhodium particles, and hydrogen, of course, dissociates on rhodium particles to form hydrogen atoms on the surface. NO can be dissociated by the assist of the co-absorbed hydrogen atoms forming OH species at catalyst surfaces. So NO can dissociate only by the assist of co-absorbed hydrogen atoms on monometallic rhodium particles. This step is the rate-determining step for catalytic NO hydrogen reaction on rhodium supported on silica. So for enhancement of NO dissociation, our strategy is at first to use bimetallic sites composed of rhodium and oxophilic metal site here. For the adjacent site, rhodium and second additive, this is oxophilic metals. Then oxophilic metal catch up the oxygen atom of NO molecule absorbed on the adjacent rhodium site. The second point is that the resultant metal oxygen bond obtained by NO dissociation, the oxygen come here, the metal oxygen bond distance, bonding formed by the NO dissociation. This metal oxygen bond should be easily reduced with hydrogen to recover the original rhodium metal sites. The third point of the strategy is to create a preferable geometry to provide a shorter distance between metal and oxygen atoms. So that makes the NO dissociation easier. In relation to the first strategy, this point, many metals show the advantageous interaction with oxygen. And again, oxygen affinity of metal may predict the easiness of the first point, easiness of the metal-oxygen interaction, and also oxygen affinity of metals may predict the easiness of the reduction of the obtained metal-oxygen bond. And this is a list of oxygen affinity of metals. These metals are listed in the table. I only the relative values of oxygen affinity of each metal oxide converted to their metal levels, the minus value and the positive value. The larger the values, the stronger the metal oxygen bond becomes. So these metals on the bottom, close to bottom, for example, magnesia, zirconia, alumina, titanium, or silicon, these metal oxides are very difficult to reduce to their metallic states. And the hydrogen levels here, hydrogen catches the oxygen of the reactant molecule, therefore the hydrogen is converted to water. So that the initial stage of reduction by hydrogen, so for example, the ratio of hydrogen, water to hydrogen, 10 to the minus 3, so the very initial stage of reduction, the level of the oxygen affinity is 26. But as reduction proceeds, the ratio water to hydrogen increased. For example, 1-to-1 ratio, the value decreased from 26 to 20, about 20 here. So these metals oxide, for example, molybdenum oxide or iron or tungsten or potassium oxide are reduced with the metallic state, but only at the initial stage, because the reaction goes on and water produced, then quickly reduction dropped, stopped. So the rhodium located here, the gold, silver, platinum, palladium, their oxide easily reduced to their metallic state by reduction with hydrogen. The rhodium located here. So the second additive metal, that oxygen metal, should be located between rhodium level and hydrogen water level. So the copper, bismuth, lead, uranium, cobalt, nickel, cadmium, germanium, tin, these metal oxides are candidates for the additive second oxidative metal to the rhodium particles. We chose tin. Another reason why we chose tin, the recent study of bimetal thin crystals present a very useful surface model for bimetallic surface layers. This is a √3 by √3 structure of platinum tin bimetallic surface layer, not rhodium, but in this case platinum tin bimetallic layer. √3 by √3, the shaded tin and white circled platinum. The diameter of tin is larger than the diameter of platinum. So the level of tin is a little protruded from the platinum level by the reason the larger diameter tin than the diameter of platinum. Therefore, nitrogen oxide, NO molecule absorbed on platinum sides, the oxygen atom of NO molecule becomes more closer to tin atoms as compared to the flat arrangement. So this is the third reason why we chose tin. we prepared the rhodium-tin bimetallic particles supported on silica support surfaces by using the selective bimetallic reaction by using tetramethyl tin vapor at 423 K. The rhodium particles, at first supported on silica and exposed to tetramethyl tin at 423 Kelvin, evolving two methanes per tetramethyl tin. The obtained bimetallic samples are further reduced with hydrogen at 573 K, and furthermore, two methane are evolved to gas phase by the hydrogen reduction. This is the final reduced rhodium-tin bimetallic catalyst supported on silica. We use this bimetallic catalyst. This figure shows the variation of turnover frequencies of catalytic NO hydrogen reaction plotted here as a function of tin content, atomic ratio tin to ratio plotted here from 0 to 1. The turnover frequencies were calculated from the amount of absorbed carbon monoxide plotted as triangles here, which is assumed to be equal to the number of surface rhodium atoms. The catalytic activity of the bimetallic catalyst with the 0.4 atomic ratio of tin to rhodium is 75 times as large as the catalytic activity of monometallic rhodium catalyst. The catalytic activity is not increased linearly, but increased in a S-shaped form. So the critical values for the tin content are around here. So below this critical value for the tin content, we observe the terminal carbon monoxide peak by FTIR and also the bridge type carbon monoxide absorbed by bimetallic catalyst. Above this tin content, we observed only terminal carbon monoxide peak. This is a surface model structure of reduced rhodium-tin bimetallic catalyst before catalytic reaction. On the basis of a stable rhodium 1-1 flame, the hexagonal arrangement shown by this structure model. The one rhodium atom is surrounded by 6 tin atoms. We observed only a linear carbon monoxide peak by FTIR, no bridge type carbon monoxide observed, suggesting the rhodium atoms are located in isolated sites. So the isolated rhodium sites surrounded by tin atoms. And according to tin KH exact spectrum, all of tin atoms are bonded to rhodium at 0.27 nanometer. And when the samples are exposed to oxygen at room temperature, all of tin atoms were oxidized, forming tin-oxygen bond at 0.205 nanometer. These results indicate that all of tin atoms are located at the surface of rhodium-tin bimetallic particles. Furthermore, the carbon monoxide absorption experiments and the transmission electron microscope image suggest the surface composition is the ratio of tin to rhodium is 3 to 1. Tin is 3 and Rodin 51. The side view of the bimetallic surface layers is pictured here. The diameter of tin is about 0.280 nanometer, and the diameter of Rodin is 0.268 nanometer. Therefore, the diameter of tin is larger than the diameter of Rodin. Therefore, the level of tin is upper than the Rodin level. Therefore, we can make the preferable geometry for NO dissociation we predicted in the strategy. So this geometry provides a shallow hollow arrangement on the Rodin side. When NO molecule absorbs on Rodin molecular form, oxygen atoms of NO molecule, this oxygen close to tin atoms as compared to the flat surface layers. So this is a structure we expected. And furthermore, we observed the direct bonding between the tin atoms and oxygen atoms of NO molecules absorbed on Rodin side by X-ray spectrum. So this is the Fourier transform of X-ray spectrum from the tin KH X-ray absorption. This is the intensity of the transform and the distance which is corresponding to the bond distance, but the phase shift is uncorrected here. The black line is a spectrum for the reduced rhodium-tin bimetallic catalyst, and blue one, the spectrum after NO absorption, NO alone. The red one, red curve here, for the spectrum under reaction conditions, NO and hydrogen at 373 Kelvin. NO absorption also at 373 K. We observed only metal bonding for reduced bimetallic catalyst before catalytic reaction, but after NO exposure or under reaction conditions, the first tin oxygen bond and the second tin oxygen bond are observed. The first tin oxygen bonds appear immediately after NO exposure on the surface at the reaction conditions. And the second tin oxygen bonds were observed by the further NO absorption on the partially oxidized bimetallic surface. Partially oxidized surface means the first NO dissociates on the surface almost instantaneously to form the oxygen bond and nitrogen bond, oxygen bonding to tin. This is the first tin oxygen bond observation. And then the second NO molecule absorbed on these partially oxidized layers. To examine the second tin oxygen bond, we took the FTIR at low temperature and at near room temperature. At 147 Kelvin, we observed the linear NO species at 1809 reciprocal per centimeter by heating this surface to 251 K. Besides this linear NO peak, the low frequency peak at 1635 reciprocal per centimeter is observed. The appearance of this band coincides with the observation of the second peak of tin oxygen bond observed in FTI Fourier transforms in X-axis spectrum. So this may be the Grease-type NO or a Pen-type NO. But by judging from the observation of the direct bonding of tin and oxygen bond. This is assigned to N-type NO. In summary, on the rolling tin bimetallic surface layers, NO molecularly adsorbs, showing 1809 reciprocal per centimeter at low temperature, observable at low temperature, at 200 K, or of course under reaction condition at 373 Kelvin. NO molecule instantaneously dissociate to nitrogen atom and oxygen atoms. Oxygen tin bond was observed at 0.205 nanometers. Nitrogen atoms recombine to form dinitrogen evolve to gas phase or react with nitrogen oxide to form dinitrogen oxide. NO comes again, and we observe 1635 reciprocal centimeter for N-type NO, and we also observe direct bonding between tin atoms and the oxygen atom of NO molecule absorbed on loading sites at 0.256 nanometer. So the catalytic NO reductions proceed by each elementary reaction steps. Back to the Fourier transform again, we discussed mainly the tin-oxygen bonding, the first T and second T. Now we analyze the metal-metal bonding in more detail. This is the curve-fitting analysis. This is curve-fitting analysis. The red one is the experimental measured X-axis oscillation, and the blue dotted lines are the curve fitting by assuming two different types of tin-oxygen bond at 0.205 and 0.256 nanometer, and then we added one tin loading or tin bond distance. The fitting is very good, showing the reliability factor of 2.7%, but still these points shown by arrows downward, deviation between the fitting curve and experimental value. Therefore, we added furthermore the different distance of tin loading or tin bonds. That is a four-way fitting. The complete refit was performed, showing very low reliability factor, complete refitting by X-axis, showing the different bonding for metal-metal bond. The first peak is 0.268 nanometer with coordination number about 6 and 0.284 nanometer with coordination number of about 3. That means I explained this model for the surface layers, top layers and the second layer, but more detailed X-axis results suggest the top layer relaxed from the ideal bulk structure. The top layer, the more separated, the distance between the top layer metal layers, bimetallic layers, and the second layer, the distance is 0.219 nanometer, which is larger than the bulk ideal separation of 0.203 nanometer. So we prepared rhodium tin bimetallic particles supported on silicon, which was very highly active for NO dissociation and NO hydrogen reaction. We presented a model structure of the rhodium tin bimetallic surface. And we presented here the first example observation of molecular reaction intermediate. And finally, briefly, I mentioned the surface relaxation of the bimetallic fluid. Thank you for your attention.
that this is using the bimetallic surface and the surface structure. So necessary are just sufficient for dissociation before the energy reduction of energy. Because if you expand the mechanism according to the atomic clocks, all the surface structure of bimetallic surface will be important.
Yes. On monometallic loading surface, that we assume the flat surface mainly because the most stable plane is one surface. The loading cannot dissociate NO below 150 degrees Celsius. And also we observe the NO linear type and the bridge type or bend type also on monometallic loading particles surfaces, but it doesn't dissociate. For NO dissociation, the rapid NO dissociation, the second oxygen type metal catching up the oxygen to form the relatively stable, but inversely relatively unstable because it's also the removed objects by the reduction. That stable, relatively medium stable team oxygen bonds are necessary for rapid dissociation.
This is a very interesting example, very good example, showing that the catalyst design, the fundamental research in catalysis can promote catalyst science and catalytic technology. I compliment you on this point. You have done a very good job. My question is it easy to hydrogenate